Gautham is a PhD student at Alberta University, advised by Dr. Rupam Mahmood. He will be presenting his work that has been published in Europe's at in last year, 2024. So, Gautham, I think you can start it.
Okay, sounds good. Let me share my screen first. Okay. Okay, so could you confirm that you can see my screen?
Yep, crystal clear.
Yes.
Perfect. Yeah. Hey, thank you. So yeah, I'm Gautham. I'm here to present our recent Europe's work, deep policy gradient methods without batch updates, target networks, or replay buffers. So my co-authors Mohammed and Rupam are also in this call. So yeah, at any point if something is not clear or if you have any clarifying questions, feel free to interrupt and then ask me that. Okay, so I'm broadly interested in agents that can learn on the fly in real time by interacting with their environment. So let me give you an idea of what I mean by that. So here in this frame, it's like you see a squirrel, and this is someone's backyard. So they have a bird feeder, right? And they have a problem where the squirrel keeps stealing grains from the bird feeder, so they don't want that to happen. So they improvised, and then they added this slinky, right? So now it's supposed to make it harder for the squirrel to climb and get to the bird feeder, right? So now the video that you're going to see, it's basically the squirrels attempt different attempts over different days to get to the bird feeder. Right, so as you can see, it's like this is happening over different days, and there's like different attempts, different squirrels coming in. But then yeah, this, I think, pay close attention to what's going on now. So this is really cool. So it's like over time, the squirrel, it's trying to figure out what it's supposed to do, and then it's adjusting how it's climbing over the rod now along with the slinky. And yeah, finally it's like it reaches its goal. Right. So now this is the kind of intelligence that I would hope to see in our in the agents that we create. So what I mean by that is you have this real-time learning ability where you learn through trial and error interactions with your environment. And again, this is super fast, right? So it's like you're reacting in milliseconds. So the squirrel here is reacting in milliseconds to achieve its goal. So if you take a moment to think about a lot of commercially available AI applications and other devices out there, so we've made a lot of progress. So you can think of these examples like an AR headset or a Mars perseverance rover or the Apple Watch or the commercially deployed robot, the iRobot Roomba. So these all have they all have AI capabilities, but a common theme in all these systems is that you have two different phases of training and deployment, where the system is frozen post-deployment, right? So if you train offline, you deploy, and if the system needs to be fine-tuned, you send all this data back to a cluster, you make some more updates, and then that's deployed again. But if these systems are capable of learning online and in real time, they can adapt right away to the non-stationarities in their environment. They can adapt to unforeseen situations. Like, for example, if you have the Mars rover, that's like a terrain that we've never seen before. And the rover should just be able to adapt to its terrain and perform better over there. And for that to happen, such learning, it must occur on device. It has to rely on the limited computational devices it has on board. So for the duration of the talk, I'm focusing just on the reinforcement learning setting. So this is the standard agent environment interaction that we're all familiar with reinforcement learning. So the agent senses where it's at, it knows where it's situated in the world, so it sees state, and then it takes an action, and the action has an effect on its environment. And that gets it to a new state, and then it sees a scalar reward. Right. So so here I'm broadly categorizing the reinforcement learning method into two broad classes. So you have batch reinforcement learning and you have streaming reinforcement learning. So with batch reinforcement learning, the idea is that all the experience that the agent sees in its world, it's stored in a replay buffer, right? So anytime you make a learning update to the neural network, what happens is this learning algorithm, it samples some data from a replay buffer, makes an update, and that is later used to interact with the environment. Right, so so there are a lot of popular algorithms which do that, like soft actor-critic, PPO, TD3. In contrast, with the streaming reinforcement learning setting, it's like these methods learn from a continuous stream of data, and they process one sample at a time, and they do not store any samples. Right, so most of the algorithms in the Sutton and Bartow reinforcement learning textbook, so the classic algorithms like actor-critic, Q-lambda, Sarsa-lambda, they are all streaming. So like in this case, what happens is you sense your environment, you act, and then you make a learning update right away, and then you're not storing any raw data. Right, so these streaming reinforcement learning methods, they are computationally cheap, and they are amenable to real-time updates. Right? And they also support on-device learning, which could be critical to preserving the privacy and the security of the user. So just a note. So for the talk, it's like I tend to use incremental and streaming interchangeably. So whenever I mean incremental, you can just think of streaming. Right, so let's think about how learning would play out in simulation, right? So in the simulator, it's like you have access to your agent state, and once you get the agent state, it's like you take an action and you make a learning update. So far, so good, and we can call this one time. So this iteration can go on for multiple steps, and maybe you get bored, you go step out for a cup of coffee, pause the simulator, you come back, and then you can resume from here, and things keep going on, right? So in this case, there's literally no difference between using a batch method or a streaming learning method. What you might see a difference would be in terms of maybe the total work clock time in terms of the whole experiment, but it does not really affect the environment. But if you're running things in the real world, that does not work anymore, because in the real world, it does not pause while the agent computes an action or makes a learning update. So I'm going to give an example of computations when things happen on a robot, right? So imagine you have a robot which also has a camera. So let's say you poll the proprioception information. So let's say it's something like wheel velocities or joint angles. And that comes in at a specific frequency. And then you also poll the images. So with this information, you have to construct an agent state now. And based on this agent state, you have to take an action. But if you're controlling the robot at a specific frequency, this means that this action has to fit within this time step, right? So in this example, we are taking an action every 45 milliseconds, which means sensing the environment and acting, they have to be within this time step duration. And so here I've left out this small chunk where it's like every time step you have like some amount of time left for making like a small learning update. So maybe what you can fit here is like an incremental update or a streaming update which is small enough that it can fit here. But if you have a learning update which simply would not fit within this control frequency, things have to become asynchronous now, right? So now maybe you have a different process. And so in this example, it's like I'm thinking of a batch update where you have a batch algorithm, it's sampling a batch of data from a replay buffer, and then it's making an update, and that takes longer than the duration of a time step. So in this case, now it's like things get a little more complicated where things are happening at different frequencies and different time scales, and they all have to be synchronized with each other, right? So let me show you an example of a real-time learning experiment here. So this is from an older paper of mine. So we have this Roomba here. So the task is simple. So you have a camera on this Roomba attached, and the goal is to reach one of these green sticky notes, right? And the goal is achieved when the Roomba is close enough to the target. And what we mean by that is, in this camera, the green sticky note has to occupy a certain percentage of the pixels. Right, so at the start, you're going to see this robot do a random policy. So this would be learning from scratch. So initially, it's just going to jitter around without any meaningful behavior. But after around 100,000 steps of training with soft actor-critic, which would amount to 2 to 3 hours in the real world, including refits and stuff, you start seeing this behavior where this robot now learns how to reach these goals just by interacting with its environment. Right, so on the top right, you have these inset videos, which is basically the egocentric camera. That's basically what the agent sees. So now the Roomba learns to look around, find a target, and then go there. Okay, so here we have, so I'm showing you the final learned behavior of a real-time learning agent. But let's look at how this was set up. Yeah. Oh, yeah. This demonstration, yes. So this is using soft actor-critic, which is batch arrow. Thank you. Yeah, so I'm going to show you how it was trained now. So here on this robot, we have this Jetson Nano. So it's like I have a tiny onboard computer, which is directly it has a wired connection to the robot. So yeah, to answer your previous questions, the details are also listed in the paper listed here. And the Jetson Nano, it communicates to a powerful workstation over Wi-Fi. Right. So in this case, on the Jetson Nano, which would be the local device, all we do is policy inference. And then we store just the actor. We just have the actor network because that's the only computation you can do over there on this edge device. Right. On the workstation, which is the remote device, you have a lot more computational resources. So this is where all the computationally intensive things happen. Right. So this is where we have policy learning, and we store the actor, 2 Q networks, target networks, and a replay buffer. Right, so now it's like you have this, we do have real-time learning, but we now have this setup where there's 2 different computers. One is an edge device on the robot, the other is a remote workstation, which you have access to over Wi-Fi. Right, so now let's think about the compute requirements for on-device learning, right? So if I'm doing soft actor-critic here, the default set of parameters. So here I want to send an action every 45 milliseconds, right? And for soft actor-critic, for a default replay buffer, I'm storing 1 million samples. So if I'm storing these low resolution RGB images of size 160 by 90 by 3, I would need about 40 gigabytes of RAM. And I'm also storing the proprioception data here. Right? And the policy inference is fine because of the Jetson Nano, a forward pass for the network we have, which is a 4-layer CNN with a couple of feed-forward layers. Inference on that just takes 17 milliseconds, which fits within the action cycle time. But if you're making a learning update, on the GPU, it takes about 60 to 70 milliseconds, which is pretty fast for us for this task. But if you try to do that on the Jetson Nano, it's on the order of seconds, which is extremely slow. And it also blocks every other compute that you can do on board. So it's like, really, you cannot do any real-time learning with just the onboard device. So one of the takeaways that we got from this paper was that batch deparallel methods like SAC, they are ill-suited for real-time on-device learning. Right, so a natural idea would be that we don't have to use the default hyperparameters of SAC. Maybe why don't we just reduce the size of the replay buffer, choose a smaller batch size, so that you can meet the onboard resource constraints, so that you can just continue to learn online. So that's something we first tested in simulation. So here, so I want to highlight that this is not a learning curve. So let me tell you what's going on. So on y-axis, you have the average episodic return in the last 10,000 steps of training. So all the plot points here trained for 10 million steps, right? And the red line here, it says it's trained using soft actor-critic. On the x-axis, you have the replay buffer size, but in the logarithmic scale, right? So on the right most, you have 1 million. On the left most, you have 10 to the power 0, which is just basically a replay buffer size of 1. So that'll be the streaming setting. So what we see here is that as you keep reducing the size of the replay buffer, the performance is drastically impacted. The performance just like pretty much drops. So, and again, each point here is averaged over 30 independent seeds. So this is not just a random thing that we witnessed. So this, we noticed that it's also true across algorithms. So we tried another off-policy batch reinforcement learning algorithm called TD3. And again, when the replay buffer size is the default of 1 million, it does really well. But as you keep reducing the replay buffer size over time, and especially if you reduce it to the streaming setting, the performance just like it just fails catastrophically. And this is also true with PPU. So PPU still has a buffer. So you collect maybe 2,000 data points or 10,000 for 10,000 steps, and then you sample from that buffer, and then you make learning updates, and after that you flush the buffer. But so far the trend holds where it's like as you keep reducing the size of the replay buffer and correspondingly the size of the batch for these deep reinforcement learning methods, the performance just degrades over time. So I can stop here just to make sure it's like everyone's on the same page and see if there's any questions. And it's over how many seats? It's over 30 seats.
Jacob says, reminds me of Grokking plots.
The Grokking
Plots.
Okay, I see. Okay. Cool. So far what we're showing is that you're using, oh yeah.
There is also different plot than that.
So in this plots, no. So in the paper, we have the learning curves as well and the variance across the learning curve. So it's like that will be listed in the appendix. Yeah. Okay. So the main takeaway here is that you have batch reinforcement learning methods, which work pretty well in their default configurations. But if you reduce them to the streaming setting, they fail catastrophically. You're not able to use them in the streaming setting. So the next idea would be that we don't have to use a batch reinforcement learning methods, but there are existing incremental learning methods, right? So why don't we try that? So there's the classic actor-critic method in the Sutton and Bartow textbook. So we're calling it the incremental one-step actor-critic here. So we're just focusing on the case where you just learn from one-step returns. So incremental actor-critic, it'll learn from a continuous stream of data. It learns one sample at a time without storing any of the samples. It uses the likelihood ratio gradient estimator. So this is what the key learning update should look like. So it's like you have the TD error delta, which is also highlighted in blue. And you would notice that this delta drives both the critic update and the actor update. Right, so you have an actor network, the policy, which can be either a continuous action policy or a discrete action policy, and the critic is just the value function. Right? So here for the actor, we see that you're taking the gradient of the pi with respect to theta. And in gray, I've also added this entropy regularization term here, because this is again commonly used for good performance. So this is a very computationally cheap algorithm. And there's examples of this working successfully. It successfully does real-time learning with linear function approximation. So now let's see how this algorithm performs on Mujoko benchmarks with deep neural networks. So incremental actor-critic here would be, it's represented by this green diamond, right? So this is pretty bad. So what we see here is that on all the 4 tasks with ant, half cheetah, hopper, and humanoid, whenever we are in this streaming setting, which is the plot point 10 to the power 0, it's like all the methods do really badly, right? And the incremental actor-critic is no exception here. It's also performing pretty badly. So this tells us that there's like a need for a robust incremental method that can leverage deep neural networks for learning in real time. So that's what we go about. So this was basically the goal that we were trying to achieve with this paper. So this is a hypothetical learning curve. This is just something I hand sketched. So here on the y-axis, you have the return. On the x-axis, you have time steps. And so red could be any algorithm that you like of your choice, which does really well. And what we are seeing is that there's this gap in performance between your incremental methods and a batch RL method. And what we'd like to see is we come up with an awesome incremental learning method, which maybe takes slightly longer to learn, but given enough time, it should be able to match the same performance as a sample efficient batch method. So with this goal in mind, we propose a novel incremental deep policy gradient method called the action value gradient, AVG, and it does not require any batch updates, target networks, or a replay buffer. So let me show you how this works. So with policy gradients, we are trying to maximize the expected value over many states. So the classic way we've been doing this is using the likelihood ratio gradient, where we are taking the gradient of the policy with respect to its parameters. So it's like you have this log likelihood ratio that you see here. But if you assume a case where we are just restricted to continuous actions, you can come up with a different sample estimator. So here, where we can directly take the gradient with respect to the Q function. So because it's continuous actions, the action would be a part of the input to the Q network now, and we can propagate the gradients through the action. So this is also known as the reparameterization gradient. Detailed proofs for this can also be found in Lan et al. 2021. So we are focused on this reparameterization gradient estimator to come up with the AVG algorithm. So here I have this cases where it's like on one side you have the likelihood ratio gradient estimator and the reparameterization gradient estimators. And on the top you have the classes of methods like incremental and batch. So when you have the likelihood ratio gradient and incremental methods, you have examples like reinforce and actor-critic. In the case of batch algorithms, you see algorithms like PPO, DRPO, actor. With the reparameterization gradient and the batch setting, we see algorithms like DDPG, SAC, TD3, but there's really no good incremental reparameterization gradient method. So by introducing this method, you're also filling a gap in the literature. So this is what the key updates of the algorithm would look like. So first, we sample an action, and note that this action sampling, now it's like A is also parameters by theta to represent that we propagate the gradient through the action. So here, this would be the reparameterization technique. So for this paper, we use Gaussian policies. So the actor would output the mean and the standard deviation. So for people who are trying to figure out what the action sampling would look like, you can think of it as mu plus sigma times epsilon, where epsilon is drawn from this normal distribution. Right. So you would notice another difference between incremental actor-critic and AVG here, which is here we have a Q network. We don't have the value function B anymore. So for the delta, you have a Q network parameterized by phi here, and it's taking in the inputs S dash and A dash. And because we also have an entropy regularization term, which shows up in the TD error and the actor update. So you'd notice that the TD error drives the critic update, but it's missing in the actor update. So for the actor update, we're taking the gradient directly with respect to the Q function. And you also have the sample entropy term here. Yeah, I'm going to hold here for a bit so that people can make sense of the math here. Okay, so along with AVG, we also use 3 normalization and scaling techniques. So we normalize the observation. We get the last hidden layer features, which would be the penultimate layer of a neural network, and then we normalize that into a unit vector. And we also scale the temporal differentiator. So I'll tell you the details of how all these are implemented in the upcoming slides. But the main idea here is that these 3 techniques, they are essential for maintaining good learning dynamics. They reduce instability, and they also improve plasticity. So these 3 methods give us a way of handling the issues that are related to having large bootstrap targets. Because with reinforcement learning, what happens is initially the policy is bad. So it's like you start seeing these small returns, but over time, as the policy improves, it keeps changing. So the target for the value networks keep getting larger and larger over time. And this is also very non-stationary. So these 3 techniques are a way. It's not the only way. So it's a way for us to handle that. So when we normalize the observations, we estimate the sample mean and the standard deviation for the observations over time. So this is just a running estimate over time. So this is commonly used with algorithms like PPO. So here we get the observation sample, and then you subtract it by the mean and scale it by sigma. We also do something called penultimate norm. For purpose of understanding, you can think of it as being similar to layer norm, except that it's basically just the last hidden layer. So once you get the post activations of the last hidden layer, you get that vector, and then you make it a unit norm. Right? So you make it a unit vector so that you do not have any exploding activations. And we use this for both the actor network and the critic network. And finally, we do return scaling. So I mean the TD error scaling. So this is from a paper called return rescaling. So this was originally made for batch algorithms, but we've adapted this to the streaming setting. So here they came up with this formula under certain assumptions where you can estimate the variance of the TD error as the variance of the reward plus the variance of the discount factor times the expected value of the squared return. So whenever you have delta in your learning updates, what we do is we scale the delta by the sigma delta that's estimated over time. And to do this, we maintain the sample mean and standard deviation estimates for the reward the discount factor, and the return. And again, for the discount factor, what we mean by the variance of the discount factor is that in this setting, so what we do is the gamma is fixed for most of the episode, but when you have the terminal state, the gamma would be set to 0. So everywhere else, it's the default discount factor that we choose. So AVG plus all the normalization scaling techniques combined, we see that it performs really well. So here, I'm showing you learning curves on 9 different continuous control benchmarks. The blue learning curve is AVG. So on the y-axis, you have the average episodic return. So these are standard learning curves. On the x-axis, you have time steps, and it goes on till 10 million steps. So the blue solid lines would be the average performance over 30 independent seeds of AVG. And the shaded region indicates a 95% confidence interval. The gray dashed line is the performance of SAC after 1 million steps. So what we see here is that AVG is the only incremental method which achieves comparable performance to SAC on most of these environments. And in fact, it outperforms SAC on all the dog domains. So it's like on dog stand, dog trot, and dog walk. We are beating soft actor-critic by a very significant margin. So here, the red learning curves SAC1, that's basically soft actor-critic, but it's reduced to the streaming setting, where it just processes the most recent sample. And for TD31, that's the same again, where TD31 is basically reduced to the streaming setting. A lot of information here, so I'll stop here for a bit to see if there's any questions.
There is a question from Jacob. What's the intuition for gamma equals to 0 after a region? I see mathematically it's equivalent. It's equivalent to setting the next Q to 0, but is there any difference?
Yeah, that's a good question. So I think for us, we are doing it just because we want to set the next Q to be 0. So we want to make sure that that's counted as a terminal state. But I'm not sure if there's other things that we gain or the other intuitions that can be found there.
We have another question. How many steps of training SAC does the grading dash find?
Yeah, so this would be the performance of SAC after 1 million steps. So if it's 10 million, I think the dash line goes up for humanoid and half cheetah and hopper. We still maintain our advantage on the dog domains, but on the others, SAC would be better. But yeah, so here also, when you're thinking about fairness, so soft actor-critic would do a lot more gradient updates because you have a lot more, so you're storing all the information in the replay buffer, and because we are doing these streaming methods, they're just using one sample at a time, and they're not really storing any of these samples.
Why is it a different number of gradient steps?
Why is it a different number of gradient steps? So, I mean, for soft actor-critic, I think the gradient steps would be the same. So, I mean, the number of, so that'll be like 1 million updates there, but then you use a larger batch. So basically, it's not that it does more gradient steps. It's reusing the samples multiple times. So it's like you're using, you can think of it as maybe using more samples to do that, but yeah. Okay, so I showed you a bunch of learning curves, but I said what did I actually learn? So this is a rendering of the learned behavior on all these environments. And again, on dog, it's like it's always like a little funny for me to see this, but that turns out that's like mostly state-of-the-art performance and of what you can expect in this domain. Yeah, cool. Okay, so here I showed you that it's like AVG is working, but now it's like I want to take a step back and also talk about an issue that's inherent to the streaming RL setting. So here I'm going to show you instability when we do not have any normalization and scaling techniques. So I have 3 different plots here. So on the leftmost plot, we have we plot the learning curve. So we are comparing soft actor-critic, AVG, and AVG minus. So when I have AVG minus, what I mean is it's basically AVG, but without any of the normalization and scaling techniques. Right. So what we see here on the leftmost learning curve is that soft actor-critic in 1 million steps, it's doing really well on humanoid. So AVG is starting to learn. It's starting to learn a decent performance, but still has quite a bit to catch up. But with AVG minus, you just see this flat learning curve, right, where it's like it hasn't really learned anything. And the other two plots here, we are plotting the gradient norms of the actor and the critic. And notice that the y-axis that's plotted in logarithmic scale now. So the gradient norms, so basically they're getting the gradient norm from the entire network, and then I'm reducing it to one value. So it's just an average over multiple parameters. And the solid lines are average over 30 seats, and you have like these thin lines, which are representations over the individual runs. So what is very startling here is that you see these huge gradient norms, right? For the critic gradient norm for AVG minus, you see them in the range of 10 to the power 12. Right? So this is not a good sign, because even if you have like thousands of updates, which are really, really good, if you have one update with this kind of gradient norm, it's going to destroy all the weights that were learned so far. So this, I think, is an issue that's just inherent to learning in the streaming setting, because you can always have this outlier experience, which just destroys everything that you learned so far. So now a hypothesis would be that to achieve stable learning in streaming methods, we'll have to balance the update magnitudes across time steps and episodes and reduce the influence of outlier experience.
There is a question.
Yeah.
Previous slide.
Yeah.
It says, doesn't SAT usually clip with the gradient to 10 by default?
Oh, it's a good question. So, Jacob, maybe I'm not sure of all implementations to it. Maybe you could also like point us to some of the popular implementations. But yeah, like, so I think there are. So with batch methods, you kind of get that in the sense that you have a batch of data. So even if you have some outlier experience, you're smoothing over that data, and then now the gradient norms are a little more manageable. And even in that case, if it's still not manageable, you have this coarse gradient clipping where you just threshold over a specific gradient norm and reduce that. So I don't. Yeah.
He says, no problem, just wondering with clipping.
So for our implementation of SAC, we're just using cleanRL SAC. I'm not sure if cleanRL SAC does any clipping. I don't think so, but I'll have to double check. Yeah, okay. So the idea here is that for streaming methods in general, let's say if you can balance the update magnitudes across time steps and episodes, it should start being more stable. Right? And we test that. So we test the same normalization and scaling techniques that are applied to AVG on all our competitor methods. And what we see is that incremental actor-critic benefits the most. It actually benefits right away. And then on a lot of environments, it matches the performance of AVG. In some environments, it's worse, but it's still comparable to AVG. With soft actor-critic one, so whenever we see this suffix plus, that means that you have the base algorithm plus the normalization and scaling techniques. So here's SAC1 plus. It does really well on Ant and half cheetah, but then the performance is a little all over the place. On Hopper, it doesn't really achieve any meaningful policy. So what it's plateaued over here, that's basically the Hopper trying to stand and then failing. It diverges right away on Walker, and again on all the other environments, it doesn't achieve any meaningful policy. And for TV31, we didn't see any improvement in performance with the normalization scaling techniques here. So this is the final result that I'd like to show you, and then we can open up for questions. But here it's we're showing AVG. It's for the first time we have effective deep reinforcement learning with real robots, only using the streaming updates and the deep neural networks. So on the left, you have this create mover task, where the goal of the robot is to move as fast as possible within this arena without crashing into the walls. So it's rewarded for moving forward, and the episode terminates as soon as it crashes into the wall, and then it gets a penalty. And the cool thing here is that it's learned solely using the onboard computer, just the Jitsi Nano on top. On the right, I have a Mujoko reacher task. The robot reacher task, but you can think of it as an analog for the Mujoko reacher. So the reward is a distance-based penalty plus a precision bonus for staying on the road. So on the robot experiments, it's like you have this representation on the monitor where the blue is the position of the end effector and the red is the goal. The red star is the goal. So that's the performance we see after around 400,000 steps of training. And these are all real-time videos. So we're playing this at 1x. Okay. Yeah, so that's everything I had. I'm happy to take any questions now. Yeah, thank you. Maybe I should. Yeah, Mohammed, I think I'll just rely on you for the questions because I can't see that window here. Or yeah, people can feel free to unmute themselves and then ask me a question.
All right. Thank you, Gautam. This is a really good presentation. It's really awesome to see how the formulations that you got here gotten you into this point of research. I will leave. If there's anyone wanted to ask a question, you can turn on your mic.
So Rupam has a question. Did you use gradient clipping for AVG?
No. So we do not have any gradient clipping for AVG. I think, yes, we didn't report it in the paper, but we did try to see if gradient clipping could be useful. I think there's an issue with the idea of gradient clipping in general, because now, so even if you have numerically very large values with gradients, if you just naively clip them with some magnitude, you can still lose some useful information because we're treating different directions or different parameters to be the same. So I think there should be smarter ways of controlling the gradients instead of just naively clipping them.
So we have another question. What's the future direction for the streaming art?
Oh, it's a good question. So it's like I had some additional slides where it's like maybe we could. Yeah, it's like I broadly wanted to open it up to discussions, but yeah. So some of the directions that we're thinking about is one. So streaming methods like be capable of fast adaptation. So it's like you can naturally think of extending them to continual learning. So you can think of environments where it's like there's a lot of non-stationarity and then rapid adaptation would be a necessity. So we can try to extend these methods to the continual learning setting. One of the things with AVG itself as a future work is that it's still a bit sensitive to the choice of hyperparameters. We have identified some sets of hyperparameters that work well on different tasks, but it still requires a little bit of tuning, especially with things like the entropy coefficient. So that's something that we are looking into. Yeah, again, if you're thinking about extending it to the continual learning setting, a natural extension would be to think about average rewards and integrating average rewards with this. Yeah, so that's I think on the top of our mind. So yeah, but I'm also curious like what other people think. It's like what would they like to use streaming learning methods with? Like, what applications they have in mind.
So Jacob, there's something similar. It looks like an amazing step forward to incremental methods. What comes next?
Yeah.
I think saying streaming RLHF.
Streaming RLHF. Yeah. So yeah, that's also a good point. So I think that would be interesting. So we have these large models now. So yeah. So right now, a lot of focus is on getting these LLMs to be like fit within a device, and then you do inference. But I don't think there's a lot of focus on getting them to learn in real time from the experience that they generate. I think that would be really interesting because in my mind, it's like if you have an intelligence assistant, let's say something like Siri, right? It should be able to adapt to your behavior patterns over time. So yes, streaming RLHF for applications in that domain where it's, let's say have smart devices or something like that. Those are natural fits. So anywhere with resource constraints and you need a computationally cheap method which is stable and efficient. I think those are natural fits for streaming learning methods.
So Jacob asked, as compute more, Moore's law continues to scale. Onboard memory compute requirement would be less. So is there any independent reasons for using incremental methods?
Okay. Right. Okay. So I think there's like different aspects of Moore's law that we can focus on here. So I think one argument could be that over time, my devices are going to get cheaper and more powerful. So it's like, why do I care about incremental methods? I can just use a batch method because it'll still fit in a couple of years' time. It'll be faster to run. But maybe we can do something better. So it feels like generally not a good idea to store all the experience in the raw data format. So it's like, as like animals, we do not really store all the information in the raw format in the brain. So instead, we have some encodings or representations that we maintain. And I think our methods should be capable of doing that. So with the compute we are freeing up from batch RL methods in the streaming setting, maybe we should use that in a different purpose. So now if you don't, if your RAM is free for, because you don't have a replay buffer, maybe you can use a larger network instead. Right, so the computation being the constraint. So maybe you can have larger networks, or maybe you can have additional components, like maybe you want to learn a model of the world, or maybe you want to maintain memory. But I think those are the kinds of components that you want to encode and use the computation for, rather than storing data in the raw format.
And also, I wanted to add a point here, which is like with incremental methods, you can scale them down as well.
Right.
For batch methods, you would break if you try to scale them down. And the point, like the main points for streaming learning is one, privacy, as Gautham said, like in many applications, you have sensitive data. So you're not able to store that. Like, for example, like medical like records or medical data, like you're not allowed to store that into a buffer. So like you wouldn't be able to use any batch learning methods. Oh, he's not audible.
Oh, yeah, I think maybe I can bring this closer. Yeah.
So can you hear me now? Hello? Can you hear me now, guys? Oh, okay.
Oh, yeah, good. Yeah.
So yeah, I'll try to repeat that again. Like streaming learning methods, they can like allow you to scale down the learning process, so you can deploy them into small devices like microcontrollers or things like that. So it allows us to have like better scaling flows in that sense, like scale up or scale down. This is the first thing. The second thing is still not clear. Okay, so
maybe I can. Yeah. So what Mohammed was trying to explain before was that so with Moore's law, it's like we can try to scale things up. It's like we are hoping to keep scaling things up, right? But in these batch methods, we have hope that we can scale it up. But if you try to scale it down, they just crash. It's like they cannot work anymore. But the nice thing about streaming learning methods is that you can scale them up and scale them down without worrying if your method is constrained to one specific setting and it fails in other settings.
So Rahul said, what about safety?
What about safety? Yeah, that's a good question. So I think that's also one of the discussion points that I have here, but maybe it's broadly under exploration in incremental methods. So right now, it's like all we have is it's like a Gaussian policy, and then you're doing on policy updates. So we're just sampling from this Gaussian policy for exploration, which basically means we have very poor exploration. And again, this is not safe exploration because the agent has to try this multiple times before it learns. So yeah, that would be a very interesting direction that I would encourage people to look at. So I think that would broadly help model free methods in general. But yeah, in this case, yeah, we're still in the early stages where I think there's not a lot of guarantees that we can give for safety.
So Karthik says edge device improvements can happen.
Right.
But the incremental method. Yeah.
Right. Edge device improvements can happen. So does he? So Karthik, do you mean in terms of computation? So you can set about running more powerful methods, or maybe I'm missing something there.
I think you mean that like it unlocks like edge device applications.
Right. Yeah, exactly. So it's like now that you have streaming methods, you can actually run on-device learning on these edge devices. And that's an area which is often overlooked.
Yeah, Rupam says we can push for more privacy respecting RL applications, try learning without storing anything. And then Han says exploration is very interesting direction as policy gradient methods do not have explicit mechanism to control exploration like UCP or Thomson sampling, which makes it more sample inefficient than other.
Right. Yeah, I agree with that. And then, also the second word Rupam was saying that's totally true, especially in this age where we have a lot of these personal devices which also have a camera and then they're recording information from the home. So now if you can do all the computation on the device, you can protect your data without having to send it to the cloud or to some third-party vendor that you may or may not trust.
So Cohere says, I think like as a reply to the privacy or the safety thing, but it would be nice if we can have some kind of layer to obstruct any poison data during a real-time learning.
Oh, I see what you mean. So here, this is more about data curation, I guess, more than. I mean, that's also part of the safety, but there's not safety in terms of the behavior of the agent itself. Instead, if the agent is adversarially attacked with the wrong kind of information or data, so you don't want it to affect the learning, right? That is interesting. But yeah,
But the normalization mechanisms are, you can see them as ways to like to prevent these kinds of poison data. Like without them, like you can have order of magnitude compared to the well.
right.
So
Yeah.
you have these like gradients become wicked.
Yeah, so now it's like this outlier experience until you keep seeing it for a very prolonged period of time, it shouldn't really affect your network because you can have a small influence, but then the moment you see the right kind of data, it should adapt back to that. So yeah, that's right. So this should at least help you partly alleviate the problem where you don't over adapt to specific kinds of experiences which are not useful for the agents.
So Hank says also I think of policy gradient is not an option here, right? Like we have a behavioral policy and perform important sampling.
Right. No, so this method is on policy, right? So that could also be an interesting future direction where you develop an off-policy version of ABG. Because I mean, if you can think about Q learning and SARSA, so SARSA is on policy, Q learning is off policy, but you're still in the streaming setting. So I would say this would be a natural future work where you can have a different kind of behavior policy and perform important sampling. And maybe that's another way to improve sample efficiency.
And also other methods from the RL book where they use explicitly important sampling because the question has.
Oh, right. Yeah. So here, so we didn't need to use important sampling ratio, so that's why we don't use it. But I think if we come up with a method which does need it, yeah, we can think about ways to stabilize important sampling ratios as well, because that's a known issue where the important sampling ratios can blow up, and it's partly why PPO clips the updates in the surrogate objective. But yes, it's possible to do streaming of policy learning.
How does incremental
Learning act on distribution shifts. So the idea here is that you adapt to the non-stationary environment. So it's like whenever you see a distribution shift, should adapt. So here we are still focused on the Mujoko. So all we have are Mujoko environments where I think you see some non-stationarities earlier in training, but then it's like once the policy is more or less settled, maybe you don't see as much distributional shift anymore. My guess would be that streaming methods adapt much better compared to batch methods when you see these distribution shifts. But that's something that was left for future work, and then we do have to verify it. But yeah, so you can imagine situations where, so in a recent Nature paper from Shubhansh and Rupam and on the loss of plasticity, they had this experiment with the ant environment where I think the coefficient of friction keeps changing over time. So that's like a way where over time, gradually, you start seeing these distribution shifts. And they did need mechanisms to make sure that the network remains plastic to adapt to those settings. I think streaming methods would also do well there, and they should be able to better adapt to those distribution shifts. But yeah, that's something we need to test and hope we can share. Yeah. Learning is much harder to handle with streaming methods compared to batch methods. Okay, so maybe Rupam, you can clarify this further, because in my mind, I think for the replay buffer, now it's like if you do experience distribution shift, you still have a lot of old stale data. And the agent needs some way of knowing that the old data is not useful anymore. But I guess you're maybe worrying about, yeah.
I think Rupam is saying that the problem is of distribution shift is much harder in the streaming learning setting, and we could solve that issue.
Right.
Like streaming learning, you have distribution shift as well, and it's solved with what we have methods.
Right. I see. Okay. Right. Yeah. It's like, I think this is what I was trying to get at.
So what I was trying to get at is the distribution shift or non-stationarity. This is actually a problem for incremental or streaming methods, and that's why the existing streaming methods, they were not working in deep reinforcement learning, right? So it had to be addressed, and those extra steps that you used, such as normalization and scaling, they helped address the instability issues due to non-stationarity. Once you address that, then we start to see the benefit of streaming learning, that it can adapt better when things change. So there are two issues here, right? So one is that the first thing, under non-stationarity, you face instability. And batch methods avoid that by storing everything in the replay buffer and sampling IID. It simply avoids that. Yeah, it contains stale data, but by averaging things out, it at least is not making updates that are going to make the agent unstable.
Okay, thanks, Rupam. I think that answers the question.
All right, that's a really good discussion. Is there any more questions? We have like 3 minutes left, maybe for the final words, maybe Gautam.
Oh yeah, thank you for hosting us. It's like I'm really happy to present. And yeah, if there's any other additional questions, yeah, feel free to reach out over email. I think my details are listed on the Cohere event and on the website too. So yeah, thank you.
Awesome. That's really great. So if there's any more questions, you can reach out to Gautam directly, like what he said. So thank you for coming, everyone. The discussion is really engaging. It's really awesome to kickstart this year with this event, and Gautam is really showing us a really good topic. And Of course, thank you for coming, everyone. So have a good day.